Now let's move to the next phase where we have a damping force. So if there's a damping force, it's going to appear as the middle term right here, the coefficient on y prime. When the coefficient on y prime is small, we have a small amount of damping. When the coefficient is large, we have a large amount of damping. Okay, so what does that do to the solutions? Well, instead of the graph that we have for simple harmonic motion, we'll have something that looks like this for a small amount of damping. And we'll have something that looks like this for a large amount of damping. Okay? Now, let's see what we have. Find the general solution for each and describe their differences qualitatively. All right, so we have y double prime plus 2y prime plus 9y is 0. So if that's the case, then our auxiliary polynomial is r squared plus 2r plus 9, which is equal to 0. That means we have the quadratic formula, -2 plus or minus the square root. B squared is 4, minus 4ac, 4 times 9 is 36, all over 2. So r is -2 plus or minus the square root of 32 over 2, and the square root of 32 is 2 root what? 2 root 8 over 2. So r is -1 plus or minus the square root of 8. So our solution here is going to look something like y equals c1 e to the negative x, or negative t, I guess, in this case, since we're dealing with time. Cosine root 8t plus c2 e to the negative t sine root 8t. So you have two terms here that are picking up the up and down action that is more or less going to mimic the first graph. So this is under damping. Okay? Now looking at y double prime plus 10y prime plus 9y equals 0, you get something that looks like r squared plus 10r plus 9 is 0. So that does factor r minus 9 and r minus 1. So r equals 9 and r equals 1. So our solution looks like y equals c1 e to the... Oops, these are positive. There we go. -9t plus c2 e to the negative t. And that is going to more or less mimic this right here, more or less exponential decay. And so right here, this is overdamping. Okay? Well, what's the difference between underdamping and overdamping? Okay? Well, the difference is qualitatively. Okay, look at these solutions and look at their graphs. You can see the difference with underdamping. You still have this mass going up and down, whereas overdamping, the damping force is very strong, and you don't have the oscillation up here. Okay, it just kind of smooths down like an exponential decay function. All right. So, what's the difference here? Well, in this case, we had imaginary roots to our auxiliary polynomial. In this case, we had real roots. Okay, what's the difference between real and imaginary roots? The answer is the discriminant. It's b squared minus 4ac. So we are going to achieve critical dampening when the discriminant is not negative, the discriminant is not positive, but the discriminant is 0. So if I let b be unknown, or representing the magical scalar here that creates critical dampening, okay, and I ask what is that value of b that generates that, we can go here. We can say what value of b makes the discriminant. So b squared minus 4ac equal to 0. So in this case, b squared times 4 times 1 times 9 equals 0. Well, 419, that's 36, b squared, so b would be equal to plus or minus 6. But remember, we said b was going to be greater than or equal to 0, so b equals 6 is the value, or is the scalar that generates critical damping. Okay, unfortunately my 6's look like b's, but this is a 6 and it's representing b. Okay, and critical damping is going to look like that, where it doesn't repeatedly oscillate up and down. Crosses through the natural length once and then returns to the natural length over time. All right, so I have this all summarized here. Underdamping is if b squared minus 4ac, a in this case is always 1, is less than 0, so the auxiliary polynomial has imaginary roots, thus this solution. Overdamping, b squared minus 4ac is greater than 0, so we have real roots, hence we have exponential terms. And critically damped, if b squared minus 4ac is equal to 0, then you have one real solution, and with multiplicity 2, consequently, your solution to the differential equation is going to look like that. All right. So that takes care of the case where there is no forcing. Okay, but what happens if there is forcing? Okay. Well, let's look at forcing but no damping. Okay, so our b term here is 0, so we're looking at y double prime plus 9y equals 5 cosine of t. What does the solution to that differential equation look like? Well, we already know, because we've done this problem earlier. That the solution to the homogeneous differential equation looks like that. But this is the non-homogeneous version, so we are going to have an extra piece. Okay? And to find whatever that particular part is, we will use our guess and check method. Since this is cosine 5t, let's use a cosine 5t plus b sine 5t as our guess for what the particular solution should be. If that's the case, y prime is going to be what? Minus 5a sine 5t plus 5b cosine 5t, and y double prime is minus 25a cosine 5t minus 25b sine 5t. Now plugging that into our differential equation, you get minus 25a cosine 5t minus 25b sine 5t plus 9 times a cosine 5t plus 9 times b sine 5t, and that's going to all equal cosine 5t. All right, so like terms, it's minus 16a cosine 5t. Like terms, minus 16b sine 5t equals cosine 5t. So this implies that b b is equal to 0 and a is going to be equal to negative 1/16. So that's what our solution looks like. Negative 1/16 cosine 5t. Now, what happens if we have cosine 3t? Okay, well, cosine 3t is now part of the complementary solution. So what we're going to do is we're going to adjust our particular solution to look like at cosine 5t plus bt, that's a 3, plus bt times the sine of 3t. And we'll do the same process again. It's not a very fun one, I concede that. Minus 3, let's take the derivative of this piece first. Derivative of at is a cosine 3t. And the derivative of the second half is going to be negative at times negative 3 sine 3t. And for the second half, we'll get b sine 3t plus bt times what? 3 cosine 3t. So simplifying this, let's see, what's the best way of saying this? We have a cosine. Let's do it this way. A cosine 3t minus 3at sine 3t plus b sine 3t plus 3bt cosine 3t. So there's a cosine, there's a cosine, so we get a plus 3bt cosine 3t plus b minus 3at times the sine of 3t, and that's y prime. Okay, and then compute y double prime. Okay, and it kind of works in the exact same way. The derivative of the first piece with respect to t is going to be 3b, multiply that by cosine 3t, plus the first piece, that's a plus 3bt, times the derivative of that. The derivative of that is minus 3 sine 3t, plus derivative of this is minus 3a times the sine of 3t, and the derivative of this second half is plus b minus 3at times the derivative is 3 cosine 3t. All right. Not the most enjoyable stuff, I concede that. 3b cosine 3t plus minus 3a sine 3t minus 9bt sine 3t minus 3a sine 3t plus 3b cosine 3t minus 9a cosine 3t. All right. That all looks right. Start looking for like terms now. we have a 3b cosine 3t and a 3b cosine 3t. Then we have 2 minus 3a's. So let's group those together. Minus 6a sine 3t plus 6b cosine 3t minus 9a. And I made an error there, that's a 9at cosine 3t minus 9b t sine 3t. And that's what y double prime p is. The differential equation, which I completely lost in all of this, says now add 9y. So 9yp is going to look at 9at cosine 3t. So that's 9at cosine 3t and 9bt cosine 3t. So we're going to add those pieces together, and we're going to get 1 cosine 3t. So cosine 3t on the right-hand side, I'm running out of paper, is going to be equal to minus 6a sine 3t plus 6b cosine 3t. So it looks like a is equal to 0 and b is going to be equal to 1/6. So our solution to the second differential equation, I'll write it in red. Y equals c1 cosine 3t plus c2 sine 3t plus 1/6. And a is 0, so there's no cosine 3t's. B is 1/6 t times the sine 3t. And that's the solution to the second differential equation. So let me show you this real quick. There you go. There's the first one, there's the second one. Now the general solution to y double prime plus omega squared y equals a cosine omega t is under resonance if w and w, if omega and omega naught are the same. The same is true if the forcing term is a sine omega t as opposed to cosine omega t. So under this system, okay, if omega and omega naught are the same, we have resonance. All right, so I'm going to stop at this point because this video is probably long enough, and on the next video we'll come back with forcing with damping.